Or the wrong page, especially just exit the class. Yeah, I've done that. Yeah, I hear tech's getting a little out of control already.
It's going up. Yeah, I mean, what's it? Alabama? 1,000 positives in a day?
Oh my gosh, really?
Yeah, it was, or maybe it was like 1,000 in a week. It's a little bit, I'm not going to say it's misleading, but I do want to know how many of those are severe cases or even moderate cases. We're not going to get that.
Yeah, they gotta get those.
Did you see, I don't know how legit this is, but a lot of people saying only like 0.6% of the COVID fatalities that only had COVID without comorbidities.
That is an interesting question. So I was reading about that this morning.
And I have like a conspiracy theory type cousin who.
No, CDC actually changed their. They issued a report. I think it was last week that talked about it, and they broke it down by death certificates.
Yeah.
What was on the death certificates? So yeah, only 6% listed COVID-19 as the only cause. All other causes had something else related to it, and you just kind of have to keep that in perspective because.
You think that's misleading?
What's that?
Do you think that's misleading?
Not really, because you can have we have infections. Severe influenza infection can lead to pneumonia. Now, those test certificates would say influenza and pneumonia. They hook them together. But if you have some other lung damage that ultimately causes pneumonia, it could be listed as pneumonia, common, and some other cause. Is that misleading? Not really. I mean, people can take it out of context. So, we talk in our parasitology class. I don't know, Nate, did you have it? Yeah, parasitology. So, echinococcus. If you had a hydatid cyst and it ruptured inside of you, you're going to have like a complete system shutdown, and it'll kill you within minutes. I mean, if that large cyst ruptures, death certificate probably would list anaphylactic shock as the cause of death, along with infection of the echinococcus. Now, did the echinococcus kill you? The worm didn't really do it, but the cyst ruptured, leading to the anaphylaxis. So, I mean, is that necessarily misleading? Right?
You can be misled by it. Yeah.
Yeah. So, I mean, we do know that there is something that's happening that is increasing clotting. And there's a paper that came out pre-release, I think maybe, that looked at that and had a possible response to that, possible drug that would combat that. I'd have to look it up. I read that maybe over the weekend or late last week. I had to find it. But again, I mean, if you had COVID-19 and you died because of a heart attack, technically you probably died of the heart attack, but was it associated? Did you have this increased clotting due to it that ultimately led to that heart attack? And how do you separate?
Yeah.
How do you separate? I take issue with the ones where guy in Florida that died in a motorcycle accident.
Well, sure.
And it was listed as COVID-19. And the rationale being, well, we don't know if he maybe started coughing while he was riding his bike and got into a car accident. Well, who's to say that somebody driving a car doesn't fall asleep behind the wheel, and it wasn't the alcohol that caused the accident, it was the narcolepsy that caused it. I mean, that's you're splitting hairs. At this point, it becomes political, just flat out. Everyone's trying to prove their point. So, yeah, that's interesting. You brought that up. 6%. 6%.
I think it was 0.6.
Yeah, 6%.
It was 6.
Only had it.
Yeah.
But as I told you, I think what's more interesting isn't necessarily the age breakdown of the deaths, but we need to see the age breakdown of the infections. All right, age breakdown of severity of infection, so severe, moderate, minor, no symptoms. And then along with that, then we need to know of those that were infected, were positive cases, what percentage of them died. Because it's fine to say that 34% of the deaths in Texas are in individuals 80 years or older. It's another to look at it and say, okay, well, we know X number of individuals 80 years or older tested positive. This is the percentage of them that died. So you kind of see that relationship. I mean, 34% of all deaths is high in and of itself, but what if we end up seeing that more than 50% of individuals 80 years or older, if they test positive, they end up dying? Very different statistic. It's actually a book called How to Lie with Statistics. It kind of shows you some of the tricks that people use. All right, so I think I asked you to do this rounding practice, and I'm going to tell you, I looked ahead because I couldn't remember what all was in this presentation. And right at the end of the presentation, I'm gonna cut out some stem and leaf diagrams. No point in going over them because I don't think I'm gonna be able to ask you to actually make one by hand. I don't want to have you make one by hand on an exam and then upload an image. So we'll probably just skip that and use histograms. All right, so I do believe I asked you to do this, and we marked off the digits. Like we're gonna round to that 3 there. We're gonna round to the 5 there. All right? Did you do that? Kind of get it done. Right. So those are my numbers. This is how I rounded. Got the rounded number, and then I also did the implied range of that rounded number, kind of to, again, prove a point that when you round a number, it could have been a range of values. And this becomes important when we start taking these numbers and using them in formulas and equations, because the error associated with it, the error is that implied range, that gets magnified throughout our calculations. So we'll see those. All right. So, do you agree with these numbers? Not too bad. All right. Rounding in R. So R can round. All right. There is a built-in default as to where it rounds. We could change that if we wanted to, but I don't. I just leave it as is. And then if I want to round at a different place, I normally just do it in my head as I get ready to report the number in a paper. But if we wanted to have R rounded for us, we can. That function is round. All right, and the function itself needs two inputs. So one is the value that we are rounding. Now this could be a single value, or it could be a vector of values. So we can have a vector of unrounded values, and we can tell R with a single command to round every single value in that vector. All right, and then digits says where we want to round it. All right, so if we want to round it to 2 decimal places, we give the number 2. All right. Now there are a couple different ways to put in these options, and I'm going to give it the option. So just to highlight these, so it takes a vector or a data point, and then our options appears after that, digits. All right, so we can say digits equal some number, or we can just give it some number. And if we don't specify digits, then R is going to go in order that values are given to it or options are given to it. All right, so I'm going to open up my R Studio, and I can start with like an RMD file. So that way we can start with our notes, basically. Start R Studio, and then this will be, we kind of skip like the variables and stuff. We'll introduce rounding, and then we'll talk about making some other graphs and tables in R. All right, so this is, move this over here. So I'm calling this data in biology. So we'll do a word template equals. All right. All right, so we are dealing with rounding values. And we're going to start with our round function. All right, that's what we're going to start with. Round function. Let me get back here. All right, there it is. So our function is round x and then digits, where x is is numeric data. And that means it could be a data point, or a vector, or it could be a data frame, or an array. Right? So basically, if we tell it R to round a data frame, it might spit out an error if you have variables that are non-numeric. Never really tried it. I don't know why you would ever use a data frame. But I know that we will round for vectors. So as we generate some random data just to make some graphs and talk about doing some randomization stuff, we'll do vectors. We'll round all of the vectors. So x is a numeric data of some type, normally a data point or a vector. And digits says where to round. All right. Now the important thing with this digits, I'm going to open up my help file here. So the important things with the digits is the default, or the positive, is always rounding to decimal places. All right. Oops. So I'm going to open up the help file here. Do my question mark round. Let me open this up a little bit. All right, and you can see that there are different functions that we'll use. So we're going to introduce the round function. All right. And in our help file, it says ceiling, floor, truncate, trunk, round, signif, if we're interested in significant figures, and so forth. So maybe a chemist might be interested in that. Physicists, I think physics uses significant digits too. Right? So digits here, this is what I want to point out. It's an integer indicating the number of decimal places or significant digits to be used. Negative values are allowed. All right? Negative values are allowed. So what does that mean? So it's a number of decimal places. That's what it defines. All right? So let's see, 4 digits, positive values refers to decimal places. Decimal places. And then negative values is to the left of the decimal point. All right? So I'm going to introduce, or I'm going to generate a new chunk, all right? And we're going to just demonstrate some of this rounding, all right? So what we're going to do is pick a very large number. Let's do this very large number with a lot of decimal places, just so we can see how that digits works. All right, so that's our number. Okay, copy this so I can just paste it. All right, so the default for round is digits equals 0. Where do you think this is going to round? So I'm going to go down here. All right, so I'm going to specify my default. The default is digits equals 0. That's kind of what popped up in my fill in the blank. So what is that going to give me when I run this chunk? 0 decimal places. So it rounds to the whole number. All right. So it rounds to the whole number. All right. We're going to insert a new chunk. We're going to round this one. Digits equals, let's say 3. How many decimal places should we get? Yeah, if 0 is 0 decimal places, we're going to go 3 decimal places. So it should round this number. It should give us 0.129. All right, it should give us 0.129. So when I run that, oops, only 2. Tricky. 1 gives us 1, 2 gives us 2. Hold on. Why? What does 4 give us? Oh, there's a problem here. Where is the rounding option? So did you see it? It's only rounding to 2. I bet that's a limit on our output. I'm gonna take this number down a little bit. It might be a limit on how many numbers it's gonna give us. So that's better.
Mine worked if I just didn't digits. Comma space.
You just did the comma space.
Yeah.
Yeah, I mean it should have worked, and it does. I mean, still mine doesn't. So I do comma space 3, and it still only goes to 2. There is an option set on here that's limiting my output. Because if I take out beginnings of it, it gets exactly what we need. All right, so I'd have to look to see what our options are. To see our options, you can do options and then open and close, and these are all of the things that are set. And what we are looking for, I think, is round. Functions. Yeah, I'll have to do a search. Maybe I can find it during our lab, and I can show you where that is. This will, I think it works on my work computer, so there may be it's separate setting, but we're going to use that big number because we're going to go the other way. So if we have a smaller number, if you recognize that something didn't quite work properly, you probably need to email me, because I'll figure out how to get this fixed so we don't get the rounding. There is a default as to how many digits get displayed. We'll see this in our statistical output when it comes down to p-values, parameter estimation, and so forth. All right, and there's ways to change it. So instead of getting, let's say, 6 decimal places, if we wanted 12 decimal places, we could get it. And we could just change the default. So I'll have to look up where to get this. In the meantime, if we specify digits equals 3, digits equals 3, then this should round to 3 decimal places, which is what, 1,000th place? All right. Now, negative numbers is the one that we're interested in. So if I do digits equals -1, where do you think we're going to round? If 0 is 0 decimal places, then -1 goes one place over. So it gets us to our tens place. Gets us to the tens place. -2 gets us to the hundreds place. So we can just kind of demonstrate that again, update it, and it gives us to our hundreds place. In this case, hundreds place is 1600 because the 9 rounds up to the 0, it changes it to 1600. All right. So rounding, pretty easy. I think the trick is recognizing that the digits always refers to decimal places, the number of decimal places that we're going for. All right. And then if we use a negative number, it takes us to the left side. So we can still round to the tens, hundreds, thousands place if we wanted to. What about these other ones? So ceiling and floor are less commonly used. All right, and that's why I'm not really going to add these into my our markdown package. I present them here because they are part of rounding. So ceiling always raises us up to the highest integer, or to the next largest integer, and floor rounds down to the lower integer. All right. Do we use these in practice? No, we don't. We don't normally use them in practice. When would we use them? We would use these if we're making a histogram by hand. If we're making our own frequency histogram, chances are our breaks are going to happen at the whole integers, and then the ceiling and the floor function allows us to quickly round all of our values either up to the whole integer or down to the lower integer. All right. Are we going to make histograms by hand? No, we're going to let R generate the histograms for us. So I'm not really going to go into using ceiling or floor, and even in any sort of slide. So I believe this slide where I have the lowest integer and the highest integer, we're really not going to use it anymore. All right. So this is, if we're not going to do it by hand, no point in really learning about it. The round function is what's important. All right, so here's a table for practice, all right, with the exception of these two in the middle. Go ahead and use R to round these 4 other numbers. So 15.679, round to 100ths place. 179.55, round to the tens place. So hundredths, right, decimals. Tens is left of the decimal, and then these last 2, 4 decimal places, and then nearest hundredths. So go ahead and round them, and then you should be able to specify the implied range just as practice. You're getting an error code for what? Attempt to use 0 variable. You have a number in there? Okay. Hold on. Around it. Here's the thing actually flows. You don't have, look at this.
I don't know what's up with that. Crazy.
Right. Any of you watching are having issues, then please type it in the chat box. Maybe I found it. How's it going? All right, so I figured out where our options come into play. So it's not necessarily rounding. R keeps the unrounded value in memory. All right. Oh, right, I was showing the help file and it was covered. Forgot about that. Here's the help file. Oops. Oh, crud, what happened? Move that over. There it is. For the YouTube people. Here's our help file. So you can go up here and type in round, and you can get to the help file. So this was our digits. Can't remember. I've got this image on. So let me show you where this round comes into play, or the output. So R keeps the values unrounded when they are in memory. All right, which is good. But the display, when it gives you the actual number to display, then it will round. So I told you that there was this option. We can see the options, all right, by typing in options in parentheses. And then what you can do is look at the option digits, which is where it does its rounding. Now, if you type that into the console and hit enter, you're going to see that yours probably says 7, because that was mine. Mine said digits equals 7, which I think then when we did this number, it was always giving basically 7 digits. All right, so we were trying to tell it to round to, the hundredths place or thousands place, but it was only rounding to the hundredths place because digits was set to 7. In order to set this and change it, I can use options digits equals, I use 15. All right, and then when I ran it, and note, digits was in quotes first, just for it to give me, to output what the option actually said. I changed digits to 15, and now, if I were to run this options quote digits, it returns 15. So now, it's going to be limited at 15 digits, which means when I go back and do this big number, 15973, period, 1288550, and round 2 3 digits, I actually get it rounding to the appropriate 3 digits. If I do it to 5 digits, it's well within my 15-digit limit. So it's not really rounding in memory, it's only rounding it when it displays it on the output. So as I said, if you encounter something like this and you're saying, hey, I want it to round, but it's not actually rounding in the correct place, please email me and I'll just probably rehash this again and say, let's change our options that you get it correct, that you can get it correct. All right, so let's go over. So this rounding practice in R, if I were doing this and keeping track of it in my notebook, I would probably do, have something like this, rounding practice, right? Rounding practice, and then I'd have my chunks, all right? And probably one by one type in, my practice values, all right? And then underneath give my implied limit. So this is, first up we want the hundredths place. So I would do around 15.679 digits. Hundredths place is 2 decimal places. So run that, I get my output, and then my implied range of that is 15.675 all the way up to 15.684. So go 5 up to 4. We're going to be simple. Again, we could be a lot more precise, but the focus of these implied limits is to show you what happens when we start using these rounded values in equations later on. So I would do that for all of it. And whoops. Oh, I don't have the answers, so I guess we're gonna do the answers here. All right, so that's number 1. Number 2, what did you get? 79.55. Tens place. Is that -1? So zeros, the whole number, -1 goes to our tens place, right? Get our answer. What's our implied range? Yep, 175 to 184. All right, that 0 is a placeholder. Hopefully you remember that. All right, so next one is round of 1.796832. We are rounding to 4 decimal places, so digits equals 4. Just use 4. All right. Our implied range is 1.79675 up to 1.79684. And our last one, round of 38962.2. We are rounding to the hundredths place. So if -1 was a 10 place, -2 gives us a hundredths place. That rounds up to 39,000. Now, implied range. What did you get for the implied range? So our rounding was to the hundredths place. Our rounding is to the hundredths place. And we ended up at 39,000. Right? That was our target. So how do we get to 39,000? 38,950. That rounds up. Or, whoops, not 69, 39. 39,040. So this rounds down to 39,000. This rounds up to 39,000. The trickery part of this was that we rounded up to 0, and that bumped our next digit up by 1. So just got to remember, got to know where we rounded, because the implied limits goes 1 digit beyond that. All right. Any questions? We got 0 for the first one. 0 for the first one. Uh-oh. We've got a question. Which first one, Katie? Copy and paste the code that you used to get that 0. We'll see it. I think we're on like a 5-second delay. We'll see. Maybe she got it fixed. All right, so we're gonna assume Katie got it fixed. Maybe. If not, oh, she got it figured out. Somebody else responded. They must be hiding out someplace else. I don't know. Casual Pint's not open now, is it?
Okay.
I mean, that seems like the ideal place to sit and do this class.
You have to sit on the
Why
right.
you have to sit outside?
Bummer. All right, so we introduced variables. Now let's talk about derived variables. So derived variables are those variables that take 2 or more independent variables and multiply, add, subtract, or divide them in some way to produce some new variable. All right? Surface area to volume ratios. All right? Just an area represents a derived variable, like an area of a square, right? You have a length and you have a width. Length and width are independent variables. All right? We multiply them together to get an area. All right? So these are derived variables. When do we use derived variables? We use derived variables when one of the individual variables doesn't capture all of the information that we're interested in getting. All right, so surface areas of a leaf. All right, the length isn't going to tell us everything we need to know about that leaf, about its ability to capture sunlight. The width isn't going to tell us everything about that leaf. But if we look at a surface area, which would be a composite of lengths and widths, tells us a lot more information and is much more relevant if we're interested in light capture. All right, another example is this quotation, overall healthy size. What does that mean? All right, does it mean looking at just at weight? Probably not, because an individual that's 6.5 feet tall is going to weigh more than somebody that's only 5 feet tall. All right, so weight doesn't really capture the entire overall healthy size component that we're interested in. Perhaps a better one is body mass index, which takes into account both weights and heights. Is body mass index a good approximation of overall healthy size? Depends on how you define good, right? All right. Some people say, live by it and say that is great. All right, that we should always use it. But what does BMI miss? Probably would be density of what? Yeah, density. Yeah, density. So yeah, muscles. Muscle versus fat percentage. Muscles are going to weigh more. And so you look at some of these bodybuilders, their BMI is through the roof because a lot of them are like 5 feet tall, but they weigh like 220, 240 because they're just so bulked up. Yeah, BMI says that they are completely unhealthy, but BMI doesn't take into account that density, and there's other aspects to it. All right, light capturability, we talked about light length versus width versus surface area. So these are all derived variables that we would use. The most common types of derived variables are going to be ratios, index, or rates. So ratios, indices, or rates. All right, ratios, again, surface area to volume ratios, sex ratios, variance to mean ratios. We're going to use a single value to express some sort of relationship between two or more variables. Now, when we work with these ratios, we typically scale it to 1. Right? We typically scale it to 1 and then express it as, some number to 1 or even possibly some percentage. So example is sex ratios. Let's say we have 59 to 48 males. Yeah, we could say the ratio is 59 to 48, but typically we scale it to 1 so that it's some number to 1. So what would that number be to 1? Pretty easy. I'm going to bring my trusty calculator over here. Oops, I think I'm covering this up. There it is. So 59 divided by 48. So I would report it as 1.2 or 1.23 to 1. 1.23 females to every 1 male. Or we can report it as a percentage. That is also perfectly fine. All right, so ratios are probably the most common type of derived variable that we work with. Next up are indices. Often these are generically referred to as derived variables. So body mass index, that's a derived variable. It's just generic. Oftentimes they refer to it as a generic term, even though your body mass index is for weights and heights. All right, but others restrict their usage, the usage of the term index, to be a standardized variable. So the one that was basically you took one variable and divided it by another variable, or it could be a combined variable. So using weighted averages or some other function, including like writing an equation and then entering those variables in just to get a single index, or even summing of numerically scored properties. All right, so it all depends on what we want to use with an index. Basically, an index would be a catch-all. All of those things that don't fit into a ratio and don't fit into a rate. And what's a rate? Basically, it's anything per unit time, per unit area, or per unit volume. All right, so these are all things. You can think about standardization. If we were interested in looking at, let's see here. Let me come up with an example. Infection. So let's say COVID-19 infections. All right. It's fine if we have if we compare schools, right? Compare ASU to Texas Tech to University of Alabama, to University of Texas. All right. It's fine. We can report individual positive cases. All right. But what good does that really do us? If every school has 100 positive cases, does that necessarily mean that every school is having an outbreak? No. Why not? Population sizes. So yeah, what we can do is we can kind of change it to a rate and say, okay, well, per capita, and say we've got 100 cases out of the total student population. And that kind of gets us down to that. Most likely rates that we're going to encounter is speed, which is a rate, it's miles per hour, or total time to complete a task. Total time to completion. So enzymes, rate of enzyme, and so forth. Now, does all of this matter? If we work with ratios, indices, or rates, does it really matter? Does it really affect how we do our analyses? Not really. Not really. Rates and ratios are usually analyzed in the same way. All right. Typically use the same tests just across the board for these derived variables. So it really doesn't necessarily matter when it comes to analyzing data. Right? Where it matters is the error associated with it. And that's why we introduced the implied ranges. That's why we're introducing these derived variables, so that you can see how we magnify error through our equation. So, advantage of a derived variable is that perhaps this variable is the only way to analyze the important property that we're after. So if we're interested in light capture of plants, that leaf area, that is the only way to really go about doing it. Perhaps we're interested in dispersion, distribution across the landscape. Variance to mean ratios, that's really the only way to go about doing it. But what about the disadvantages? It's relatively inaccurate, and we're gonna show you why. So what we'll do is stop here, and we'll pick up with these implied limits, talk about the rest of this, and then we'll see how far we get in this presentation in lab. All right. All right. Just to give you a heads up, I have a platelet donation today, so if you want to stay in lab and work on anything, you're free to do so when we finish up at around 3 or so. But I will probably take off around 3:15 or 3:30 so I can get to my platelet donation. And for those of you that don't know, if you go to Vitalent, donate blood or platelets or plasma, they will automatically do an antibody test to see if you've been exposed or infected with coronavirus. I'm 3 for 3 negative. We'll see what I am this time. All right. 2 o'clock later today. See y'all.